In this question, we have to define and explain certain aspects of certain stochastic processes. The first one is the Poisson process. So, um, we define the Poisson random variable as this: the number of points n of t1 comma t2 in the interval t1 comma t2 of length t equals to t2 minus t1 is nothing but a Poisson random variable with parameter being lambda t. So p of n of t1 comma t2 equal to k is equal to e of minus lambda t to the power of k divided by k factorial. If the intervals, say t1 comma t2 and t3 and t3 comma t4 are non-overlapping intervals, then the random variables n of t1 comma t2 and n of t3 comma t4 are independent random variables. At any time moment t, there is no more than one Poisson point, and using the points ti, we form the stochastic process x of t equal to n of 0 comma t. So we have x of t and t. So this is x of t. Um, Regarding some of the properties, the first order probability mass p of x of t equal to k is equal to e of minus lambda t power of k divided by k factorial. The mean e of x of t is equal to lambda t. Autocorrelation r of t1 comma t2 is lambda square t1 comma t2 plus lambda times minimum of t1 comma t2, and the covariance c of t1 comma t2 is given by lambda square t1 comma t2 plus lambda min t1 t2 minus lambda t1 into lambda t2, which is lambda minimum of t1 comma t2. We see that the mean is it depends on t. It's a linear function of t, so as time increases, the expected number of buses also increases, and the autocorrelation depends on this term minimum of t1 comma t2, which is derived from the property of independent increments. Up next we have the Poisson increment process, which is defined as y of t is equal to x of t plus e minus x of t divided by e, where x of t is a Poisson process. Some of its properties are the first order probability masses given by p of y of t is equal to n divided by e, which is equal to e of lambda e to the power of n divided by n factorial. The mean is e of y of t is equal to lambda. Autocorrelation is given by lambda square for modulus of t1 minus t2 greater than or equal to e, or lambda square plus lambda by e minus lambda mod t1 minus t2 divided by e squared if modulus of the difference is less than e. And the autocovariance c is equal to 0 if this modulus is greater than or equal to e, is equal to lambda by e minus lambda t1 minus t2 mod divided by lambda square if this modulus is less than e. Also note that this expression right here is basically it's a triangle with area lambda, and it's independent of e. But if e goes to 0, then the triangle pretty much becomes an impulse with an area of lambda. The next one is point impulse process, and it's defined as z of t is equal to dx of t divided by dt, where x of t is a Poisson process. So it looks like this. This is z of t. Ti. And some properties. There's no definition for probability masses, but the mean is e of z of t, which is equal to lambda. The auto correlation is lambda square plus lambda times delta t1 minus t2, and the auto covariance is lambda times delta of t1 minus t2. Also note that uh, a process, if we take z of t minus lambda, this process has mean equal to 0 since z of t has a mean 0, and autocorrelation uh, of this process would be lambda times delta t1 comma t2. So the the process z of t minus lambda is a white noise. The next one is a semi random telegraph signal. It's defined based on the Poisson points. So x of t is 1 if k is even in the interval 0 comma t, and it's minus 1 if k is odd in the same interval, where k is the number of points as defined from the Poisson random variable. Properties: first order probability masses p of x of t equal to 1 is equal to e to the power of minus lambda t, e to the power of lambda t plus e to the power of minus lambda t divided by 2, and p of x of t equal to minus 1 is e to the power of minus lambda t e to the power of times e to the power of lambda t minus e to the power of minus lambda t divided by 2. Mean is e to the power of minus 2 lambda t, and autocorrelation is e to the power of minus lambda times modulus of t1 minus t2. Autocovariance is e to the power of minus 2 lambda mod t1 minus t2 minus e to the power of minus 2 lambda modulus of t1, no, not modulus, just t1 plus t2. Note that p of x of t is equal to 1. This is equal to 1 minus e to the power of minus 2 lambda t divided by 2, and this value goes to 1 by 2 when t goes to infinity, which matches our expectation. The mean also goes to 0 when t goes to infinity, and that matches our expectations too. The autocorrelation, this goes to 0 as this modulus as t1 minus t2 goes to infinity, and it makes sense because as t1 and t2 are far away, x of t1 and x of t2 are less correlated. Next we have the random telegraph signal, which is defined as a times x of t, where x of t is a semi-random telegraph signal. P of a equal to 1 is equal to 1 by 2, which is also equal to p of a equal to minus 1. Properties: the first order probability masses is equal to 1 by 2. P of y of t is equal to 1 by 2, which is also p of y of t is equal to minus 1. The mean E of y of t is equal to 0. Autocorrelation is equal to e to the power of minus 2 lambda modulus of t1 minus t2. Autocovariance is equal to e to the power of minus 2 lambda modulus of t1 minus t2. The fact that p of a equal to 1 is equal to p of a equal to minus 1 is equal to 1 by 2, and the fact that the mean is a constant makes us think that um, the random telegraph signal is stationary in the strict sense. Next is the random walk. If we toss a fair coin n times, and if k is the number of heads in the n tosses, then x of n of t is equal to k times s minus n minus k times s, which is 2k minus n times s. The first order probability mass is given by p of x of t is equal to xn of t, capital T, is equal to rs is equal to nc n plus r by 2 times 1 by 2n. For t between nt and n plus 1 t, the mean is 0. Autocorrelation is e of x of n t into e of into x of mt, which is minimum of n and m times s square. Autocovariance is e of x nt into x mt, which is nothing but minimum of n and m times s square. Note that in the probability masses, as n goes to infinity, we will get a Gaussian density, and from the property of independent increments, um, we get a term minimum of t1 comma t2 in this form in the autocorrelation function. The last one is the Wiener process, which is defined as limit t tending to 0 s square by t tending to alpha n tending to infinity x of t, where x of t is a random walk. Properties: first order density function f of w comma t is equal to 1 divided by square root of 2 pi alpha t times e to the power of minus w squared divided by 2 alpha t. The mean is 0. Autocorrelation is minimum of t1 and t2 times alpha, and autocovariance is also minimum of t1 and t2 times alpha. Note that the Wiener process Wt, um, for a Wiener process Wt, W naught is equal to 0. Um, it the Wiener process has independent increments. It has Gaussian increments, as in Wt plus u minus Wt is normally distributed with mean 0 and variance